Hi everyone. So I needed to start this video with my face so that I could show you a little activity we did in class yesterday. So my in-person classes, instead of doing the energy skate park that y'all did, they played around with these popper toys, right? So when we start having this discussion, the first example I'm going to use is of one of these popper toys. And then we will move on to one of a roller coaster, which is very similar to the Energy Skate Park that you did yesterday. Okay. You may or may not have played with one of these before. This bottom mesh part is elastic, so it will compress and it could stretch in the same way that a spring does. So this bottom mesh part is going to be a very similar idea to a spring, if not really an identical idea to a spring. Okay. So I can compress it, okay? And then after I compress it, when I let go, it will shoot the popper toy up into the air. It will stop and then come back down to the ground. So if you haven't played with one before, I want to kind of show you. Let's see, get the popper on the screen. Okay, so what I'm talking about. Now, we're not going to be able to see it go all the way up because my camera doesn't go that far, but we can at least see the front part and the part way up. Okay, so I'm going to scrunch it down and then I'm going to let go. It moves up and then it came back down. So it all happened kind of fast, but you can see it come up and then it kind of came back down and fell over in front of me. Okay, so when this is going to be, again, my first example that I talk about in our conservation of energy discussion, and then we'll swing back to one that's similar to what you did in your energy skate park activity. So let me see here. I want to get myself off of the main screen. I'll end up staying over here in the corner for this discussion. Now, so I can see my screen and where I'm writing, I'm going to pop it up. This is why I don't normally keep myself on the screen when we have a video, because it's just like a little bit of an awkward angle. But that's all right. So now hopefully you can see my screen here, and we're going to talk about the idea of conservation of energy. So I know this is something that you have talked about before in your other science classes growing up, elementary school, middle school, all of that stuff. We will give energy more of a formal definition a little bit later. So once we start talking about work, then we'll be able to give it like the textbook definition. But really, energy is the substance. It's the thing that makes up everything in the world. It makes up our ability to move, our ability to light things, our ability to heat things. It's this driving substance for everything that we're doing. Again, that's not a very technical definition, but that's where we will start. And then we'll swing back a little bit later in the week when we start talking about work to give it just more of an actual definition, okay? But for now, we know that this idea, this substance of energy, it is conserved, okay? But it can be transferred from one form to another. So I have a bunch of different types of forms of energy. I made my in-person classes yesterday make a list of ones that they knew, and it was just long. Like you probably in your head right now are trying to list off all the different ones that you've heard in your life, and it's a long list, okay? We will focus mainly on these 4 types here that I have already typed out, okay? So these, for the most part, you have probably heard of them before, okay? I'm going to start by giving them a definition and an equation, and then we'll apply those ideas to a couple of different scenarios. So we have gravitational potential energy, kinetic energy, elastic potential energy, and thermal energy that we're going to focus on. Something that I noticed coming into this class is you probably just want to call it potential energy and not do any sort of distinction between what I'm going to call gravitational potential energy and elastic potential energy, which is fine, okay? But there can be multiple forms of potential. It's not just, I want to be a little bit more specific than just calling it potential. So this gravitational potential energy comes from being above the ground, okay? So any sort of potential energy is named that because it gives you the potential to move, okay? So kinetic energy would be our energy when we are in motion, and then potential energy gives me the potential to move, okay? It gives me the potential to have that kinetic energy. So if I hold something above the ground, it has the potential to fall to the ground, okay? And if it's falling to the ground, then that is motion. That is kinetic energy. So it's giving you the potential to have that motion. So and it's called gravitational potential energy because the thing that's going to make it move if you were to let go would be the force of gravity. So holding it above the ground gives it the potential to move towards the ground because of the force of gravity, okay? So these equations, all three of these are going to get an equation. Thermal energy is not. We'll kind of deep dive down into that. But for both of our types of potential energy that we're looking at and our kinetic energy, I'm going to just write down the equation and then we will analyze some units afterward, okay? So I'm not going to derive them in the typical form that we've derived most things, but this gravitational potential energy, I'm going to label that E sub G. Okay, so just like I labeled every single force a capital F sub something, I'm going to do that same thing with energy. It's always going to be an E sub something. Okay, so I call gravitational potential energy EG, where like a more traditional label for it, I'll kind of write it up here, would be GPE. You'll see that a lot for gravitational potential energy. Okay, but again, in AP Physics 1, we're just wanting to do it as a capital E sub something. So it's capital E sub G for gravitational. Okay, and if I wanted to calculate that, I could do M G Y. Okay, so mg is going to give us our force of gravity. So that's the thing pulling you down. Okay, so that makes sense to want to put that into our amount of energy we have coming from the fact that the force of gravity would pull down on me. And y is going to be our height from the ground. So if I increase the height from the ground, I increase my potential for motion. I increase the potential to have a larger velocity when I reach the ground. So we have our mass, our acceleration due to gravity, and then y being our height above the ground. Okay. Now, if I look at units here, my mass is measured in a kilogram. Acceleration due to gravity is an acceleration, so it's a meter per second squared, where the height above the ground is a distance, it's a height, so it would be a meter, okay? Now, I could combine those and make that a meter squared over a second squared, but I want to do something slightly different. So if you remember from when we were doing forces, and we first derived the unit of a Newton, we said that a Newton was a kilogram multiplied by a meter per second squared. So that means that this right here, this chunk, kilogram meter per second squared, that is a Newton. So I get a Newton times a meter. And just like we named kilogram meter per second squared a joule, because that's not a joule, that's where I'm going, a Newton, because kilogram meter per second squared is a mouthful and you don't want to say that all the time. They did the same thing with a Newton times a meter. They made a Newton times a meter a joule so that they didn't have to say Newton times a meter every time. So it's a joule. I'm going to write it as a capital J. Okay. So energy is measured in joules. So each of these equations that we're about to lay out should end up with the same unit of a joule. Okay. So then our kinetic energy is the energy an object has when it's in motion. So it has to be moving to have this kinetic energy. I'm going to label kinetic energy E sub K for kinetic energy. Just like we said, another way that you'll see gravitational potential energy written is GPE. Kinetic energy you see a lot as just KE. Okay, but I call it E sub K because I want to keep all of my labels similar. Okay, but the kinetic energy, that's equal to 1/2 m mv squared. And I found that that's an equation that a lot of y'all recognize from using it before. So we have our kinetic energy being 1/2 mv squared. Okay? And if I look at the units here, then again, I have a mass, which is a kilogram. And I have that times a meter per second squared, which I could say was the kilogram times a meter divided by a second squared, which looks identical to what we were just doing over when we were looking at gravitational potential energy. So this also would be a Newton times a meter. So this would also be a joule. So that checks out. Our units work there. Okay. So then now we have our third kind here, and this is the elastic potential energy. So this is the energy that is stored in a spring or anything that is elastic. So just like our popper toy that I was showing you earlier, okay? So we said that the bottom of this popper toy works very similar to a spring, where it's elastic and it can compress or it can stretch, okay? So if I compress this and I let go, the popper toy is going to move, okay? So by compressing it, I'm giving it the potential to move, right? So just like our gravitational potential energy, the potential to move there was coming from the force of gravity, right? Here, the potential to move is going to be coming from the force that the spring or the elastic material is going to apply, right? This doesn't stretch quite as well as a spring, but the same thing, if I were to stretch this on a spring and then let go, it would snap back, right? So either way, compressing it or stretching it, the spring or the elastic material would apply a force onto the object, which would make it move. Okay, so by compressing it or stretching it, I'm giving it the potential to move. Okay, so I took a little bit of an awkward pause there in the video because I have something in my eyeball. I think I'm getting a little better now, but I'm not sure exactly what I was saying. Okay, so, but I know it was something, you know, we were given this scrunching it or stretching it and giving ourselves the potential to move, which is what we said that potential energy is. That's the definition of potential energy. So for this elastic potential energy for our equation, I label it as E sub S. That is a bigger marker than I was using before. Let's change. Okay. E sub S for energy from a spring, because most commonly we're going to use it as a spring and not just an elastic material like this popper. Okay. But either way, they have the same equation. So this energy from the spring is going to be equal to 1/2 K x squared. And we will do a deeper dive derivation of this equation next week using a graph, okay? But for now, if you remember the equation for the force from a spring, which this force from the spring is what's giving it the potential to move, our force from a spring was equal to K delta X, where K was the spring constant or the elasticity of the spring, and X was the how much you stretched or compressed it, okay? So these are the same two values. K is the spring constant, and X is how much I'm stretching or compressing the spring or the elastic material. I'm just dropping the delta because most commonly you don't see this equation with the delta in it. So if I look at our units here, K, if force of spring is equal to K times delta X, then K would be the force over the delta X, which means that K has a unit of a Newton divided by a meter, or the force over the distance, times our meter squared. So then this meter will cancel out one of those up top, and it is left with a Newton meter, which we said is a joule. So all of those units check out. This video is about to run out, so I'm going to pause and then I'll pop back in with a second video and pick up where we left off.